This is the second video in a two-part series showing how to use the moteus C++ library to implement a gravity compensation demonstration. The first video covered a 1 degree of freedom version, and you can find a link to it in the description below. Here in this video, I'm going to pick up where we left off, making a version of the example with 2 degrees of freedom. With that example out of the way, the next one I want to attempt is a 2-link kinematic chain. This will require both a more complex method of calculating the torques, and we'll have to command more than one servo at a time. The hardware for this is basically the same as that for the first demo. I'll just attach another replica of the exact same beam to the second motor that was acting as the dead weight in the first demo. So we'll screw that into place and clamp it down. Once that's in place and clamped down, we'll attach a dead weight to the final end rather than yet another motor. So here I have a 3D printed bracket with a 200-pound test mass press fit into it. And so we'll bolt that into the dev kit slot at the end. There we go. That's all in place, and now we have our 2-link kinematic chain. Play. Before starting to code, we need to first assign a unique ID to the second servo and make sure they both communicate. To do that, I'll connect the FTCAN USB to the second one, and then change the ID.ID to 2, and then immediately restart TView with the ID 2. Once that is done, we can issue the conf write, which will allow us to save that ID across power cycles. Now we should be able to connect the cables in the daisy chain configuration. So I'll connect the FTCAN USB to the top, and then we'll connect the daisy chain cable from the top down to the bottom. Now that that's done, we should be able to fire up TView with both servos and see they both respond. Let's check the position of both. Likely the second one we're going to have to set the 0 for, just like we did for the first one earlier. Sure enough, the second one's position when it's hanging straight down is around 0.33 or so, and we need it to be 0. But they both have a position, and at least the sign is correct. When we move the second one clockwise, it goes positive, and negative for counterclockwise. And same for the first one. Since those seem reasonable, we can stop TView and set the 0 offset for servo ID2. So that'll be the same moteus tool, ID2 --0 offset. We'll do a final recheck of TView to make certain that those positions are as expected for both ID1, the top motor, and ID2, the bottom motor. And sure enough, they both are very near 0. And they both wiggle, and they apparently have the correct sign. And they oscillate nice and freely when there is no control on them. For the software, there are 2 unique aspects to this example. First is how to calculate the required torques, and the second is how to communicate with more than one servo at a time. For calculating the required torques, we need to solve the inverse dynamics problem. This is similar to the inverse kinematics problem, or IK problem. In IK, a given end effector position and orientation, you need to find the joint angles to achieve that end effector position and orientation. For the inverse dynamics problem, you're giving the end effector position, velocity, and force. And from that, you need to find the joint angles, the joint velocities, and the joint torques. Here we have a slightly modified version in that we know the joint angles, but we need to find the joint torques to achieve a force. There are many libraries which can solve the inverse dynamics problem. The Quad A1 uses Dart internally, the Dynamic Animation and Robotics Toolkit. Another popular option is the Drake library, or Drake system. For the purposes of this demo, I wanted to try out Pinocchio to see how hard it was to use. Pinocchio has a permissive license, and on paper is not too hard to use in other projects. Here, I spent some time trying to integrate it into the CMake project without installing using fetch content, but ended up giving up. It seems that since fetch content relies on every package and its dependencies to properly namespace all targets, it'll probably be a decade before you can reliably use it. So here, I used the Ubuntu robot packages found at, through this link right here. So I followed these instructions listed there to install it on my Ubuntu system. Once I had done that, then you can go to your cmake.lists and just add a find package, Pinocchio. And while we're in our cmakelist.txt, we'll add a new target for our second demonstration, Gravity Comp 2, which will just be a single CC file. It'll also link against moteus, and we're also going to link it against Pinocchio, which is Pinocchio, : Pinocchio. I'll initialize a new C++ file for this example, the one we just listed, gravitycomp2.cc, and we'll get started with the boilerplate. We'll copy some of it from the first example. So those initial headers we will all need. And to use Pinocchio, we need to include its headers as well. And I'm going to find its headers from an example in one of the Pinocchio examples directory. And I had one that was an inverse dynamics without derivatives, which doesn't seem to exist in the current version of Pinocchio, so we'll just use the inverse dynamics with derivatives as our baseline example, which will be close, and then we'll fix up the differences later. And so those are the includes we need to use from this example. So we'll paste those in to our code. In that example, they load the robot model from a URDF. However, I want to, for this case, just build it directly in code because it's not that hard. And so there are some examples for Pinocchio building things in code. The sample models.hvp has a build manipulator, which builds a 6-DoF kinematic chain. So we're just going to include that header file in order to get everything that it might possibly have needed as well. So we'll start with our main, which is going to look very similar to our old main. In fact, I'll just do our return 0. And let's go and copy some of our bits from the other example over. So they're using namespace mjbots and the same argument processing that we had before. And now we're going to see if this will build. And it looks like it was not able to find Pinocchio. And the reason is the robot package version of Pinocchio does not install it in the standard system library, but in opt, somewhere in opt. So I'll just use set CMake prefix path to tell CMake where it can find the robot package versions of installed packages, which is in opt open robots. And we'll try that building again and see if we're able to find Pinocchio. And sure enough, it was able to find it this time. Once again, complain we don't have a minimum version defined, but I don't really care. Great. We can run it and verify that it should have the same command line help that we got before, and it does. So now I started work, but let's go and look at the actual example and pull it up so we can work from it while we're building ours. So we'll find that example again, the inverse dynamics. And let's copy that link and stick it over where we can see it while we're coding. Because what we need to do is at least instantiate the base classes that Pinocchio will need to operate, which is the model class. And the model is what holds the structure and all the data. They use that build model from the URDF. We're going to make a local build model, which will do our actual building of the 2DoF version. We'll make that in a second. And then you also need a data class, which takes the model as an argument. So now we'll go up and make an anonymous namespace to construct our build model function. Now our build model function is going to closely mimic the one from the parser's sample models in the Pinocchio directory. So we'll go into parsers, sample models, and the build add manipulator, which is what they use to add a 6DoF manipulator. So we're going to mimic that in our build model. And so for that, we need to have the same template arguments. We don't necessarily have to, but because we're not using the templated versions, but it certainly saves time to just use the templated versions and figure out what the default template parameters are. So we've got those template parameters and our function name, and then the only argument we need to take is the model. And we don't really care about the other ones. So the model is the thing that's templated on all those arguments. I guess we could have just done it off of the untyped model and it would have been fine too. But I'm already down this path, so we'll just stick to it. We could have used the untemplated Pinocchio : model as our argument. Let's scooch that over so we can actually see all of our own code. Now we'll make the type aliases for the same types that they use, just using the using directive for being slightly more modern. So the M they didn't use, but I did because I don't like typing models so much. So JC will be the joint collection, and CV will be the config vector, which is basically the state, so the position of the joints. And then TV will be the tangent vector, which will be either the velocities or the torques. Or it's used for both velocities and torques. And so that will be the JC tangent vector. And we get to use type name because C++ is silly and can't determine that that's a type otherwise. Or can't determine that joint model Rx or JC is a type. So now we're going to make the IDX variable, which is effectively the reference to what the next degree of freedom will be in our model, which we'll use when we're constructing it. The SE3 is a three-dimensional transform that is a translation and rotation in 3 space. And so we're going to define one to describe the relation between the base of each joint and the tip of each joint, which for our 2DoF, 2 degree of system, will always be no rotation and just moving in the z direction by the length of the beam, which in our case is 15 centimeters. So for both lengths, it'll be the same. The inertia class lets you store the mass and the rotational inertia. We're going to start with 0.33 kilos for the first link, and that mass we're going to assume is a point mass at the location of the tip. And for the rotational inertia, it doesn't matter too much because we're not going to be feeding any velocities or accelerations into Pinocchio anyway. So I'll just pick a random small value for the rotational inertia. Now we'll declare the inertia for the second link because it will be slightly different, at least the mass will be. It will still be a point mass at the end of the link, and the rotational inertia will still be small, but we're going to start with a 0.23 here, since we have a 200 gram mass plus some 3D printed scaffolding. Now, following the Pinocchio example, we'll construct our limits for angular position and velocity. The angle ones there were for 180 degrees or minus pi to pi. We'll just make ours be a little bit bigger because why not? So I'll use minus 4 to 4 for the position limits. And then for the velocity limits and the torque limits, we'll use 10. I suspect the velocity limit is in radians per second, and the torque limit is in Newton meters, and 10 is fine for both for our examples purposes. Now we're going to follow their example to add a single link in the kinematic chain. So there are 4 functions we have to call. First is add joint, where we pass in the index and get a new index and tell it what type of joint it is. And so we are going to use a joint that rotates about the y-axis. The next point in the joint will be our link distance and translation away. We'll get a name for it, and then we'll use all the limits, which are going to be the same for both of our links. So the torque, velocity, and position limits. I've got semicolon, and now we'll do the other 3 calls, which are just copying them without having any clue what they're doing necessarily, aside from knowing that they need to exist. Appending the body to the joint, adding the joint to the frame, and adding the body frame. So we'll do all 3 or all 4 because it seems like they might be necessary from the example. Great. So that's our first link. Now we're going to copy all that and do it again for the second link. So this will be the link 2 joint with the inertia from link 2, and it'll be the name of link 2. And that theoretically should build our Pinocchio model of our 2 degree of freedom kinematic chain. To actually use that model, we want to pass in positions and determine what forces are required to counteract gravity. So to do that, we will have to go back to our initial example, and we'll build the input structures, which are just going to be dynamically sized eigenvectors for the position, velocity, and acceleration. And I'm going to call the RNEA function from Pinocchio, which is not in this example, but I said I will do this from a slightly different version. And I happen to know that function is just one that takes the same arguments, but doesn't take the output for the derivatives, because we don't need those. All we want is the torques. So, and it returns the torques in a vector. So we're going to print out those torques, and our velocity, initially our position, velocity, and accelerations are all 0. So let's see first what we have to do to get this to compile. So it looks like line 25 is the first problem, and it looks like probably matrix needs to be matrix 3, because this is a 3 by 3 matrix, and SE3 matrix isn't an actual type. So we'll fix all our matrices to be matrix 3. And the next is 28. We have ilink 1, should be actually ilink 2, because we have 2 different variables. And we didn't actually include the right header to get RNEA, so we'll include the correct header. Now we can try compiling again and see what we get. Bingo! Compiles. Now if we run it, we should see with 0 positions and 0 velocities and 0 accelerations, our torques need to be 0. Big surprise. So let's test something a little bit different and change the first link's position to be 0.1 radian positive, which should result in negative torques required on both joints. And that is correct. We've got negative torques. So next we'll try the second joint being positive, which should result in a negative torque on the second, and probably a negative torque on the first 2. Yep, same negative torque on both, which makes sense. All right, so that looks like it's reasonable, and I think we have a model built. I'll consider that working, and now we can start working on the moteus parts. So here, rather than using the controller's set position, we're going to instead directly construct grab the constructed transport by using controller's make singleton transport. So this will make one if it doesn't exist and return the only one that's there if one already exists. And default arg process will make one. So this will we don't have to pass in the arguments again. We can just pass anything, in this case an empty list. And that'll give us the transport which was constructed from the command line arguments. And the transport is what is used to send and receive can frames. And since we want to send more than one frame at a time, we have to get that directly to send them. And like before, we also will need to set the options to our controllers. So let's pull back up our example here, our first example, and we're going to need the same resolutions because we're doing the same thing. We're sending pure torque mode commands. But unlike the last time, we're going to put our controllers in a vector. In this case, a vector of shared pointers of controllers. And we'll just inline initialize that with make shared for controllers, and each one will get a unique options returned from an inline lambda, and the unique options will just make a copy of the common options we have up above, which I should rename at this point. We'll rename it to options common, because that'll be the options that are common to both controllers. And then we don't actually have to change anything for the first one, but I'll just set ID to 1 to be clear that this is the one for ID 1. That way the second one will be the one for ID 2. And that's the only thing that's different between our two controllers. We'll send the same resolutions and query the same resolutions for both. Just like in the previous example, we want to set stop to clear any faults, but here we don't have just one do-do, we have multiple, but we don't actually have to send them simultaneously for this. We'll just do a range 4 over controllers, shared pointers, and use arrow set stop to call set stop on each of them in turn, which will have the same effect. And just like before, we'll copy over our position command, so we have a default position command, because it's going to be the same. And for our general structure, we're going to have a regular old C array to hold the torques that we're going to command. And there'll be 2 vectors of can frames. One to have the frames that are going to be sent out, and one to have the frames that have been returned. And we'll declare those vectors outside of the while loop so that in steady state there won't be any dynamic memory allocation going on, which can really cause in the real-time world, dynamic allocation causes processes to have terrible real-time performance. And so the easy trick is just to do all your dynamic allocation outside your critical loops. And one way you can do that with the vectors is just to keep them around, because they won't free stuff unless you go to extreme lengths. So we'll do our same use sleep at the beginning, just like we did before. And at the start of each loop, we'll clear our send and receive frames. So we start from a blank slate of no elements. And now to populate our send frames, we can just loop over the size of all the controllers. We're going to use an index variable so that we can also jointly index into our torque command array from above. So we'll set our default command. We'll update the feed forward torque to be the torque command for servo I. And then let's delete that, and we'll call controllers I make position. And so as I said before, the make variants of the commands return a can frame to be sent later. So here we're going to take that can frame and stick it onto the send frames vector. Now we need to call the transports method. And so I'm going to open up moteus transport.h so we can see what that method looks like. And there are 2 of them. There's a cycle and a blocking cycle. The cycle is asynchronous. Blocking cycle will be easier for this. Blocking, it waits until all the responses come back and then returns. And it takes 3 arguments. The first is a pointer to the first frame to send, and then there's the size. That way any contiguous set of frames will work. And then you need a pointer to the vector to hold the replies. And so once that has completed, we have 0, 1, or maybe more replies from each servo. And so you might get none if there was a timeout, or you might get more than one if you had a timeout previously that was spurious. So just like we're going to make a little local function called findServo, which will look through there for the frame from that given ID. And we'll store those in maybe servo, because I think we're going to make this return an optional. So because there may not be one from that ID in the list. So we'll return an optional, I guess we'll probably return an optional query result, because we can parse it in this function too. So let's do that. And it'll be findServo, and it'll take a vector of canFD frames. Now, if there happens to be more than one from the same ID, we want the latest one. So to do that, I'll use, instead of a range for, I'll use the iterator for over the r_begin and r_end of the vector. That way we can loop over it backwards, and the first one we find will be the last one, which is the one we'll return if it exists. So then we can just check if the source of that frame is the ID we're looking for, then we will return it. We'll return the parsed version of it. So for parsing, if you go to moteus protocol, you can find all of the command modes. So there's position mode, query, VFOC mode, and inside that query structure, we saw the result, the format, and near the bottom is the parse, which takes a pointer to can data and the size of the can data and returns the query result that we want. So we'll use moteus, MJBot's moteus query parse, and the data and the size from the can frame of interest. And then if we make it to the end of the for loop with nothing, we'll just return nothing and return an empty optional. And we do need to include optional. So our missing replies handling is going to be pretty much the same as our other example. So let's pull that up. The only difference is that we're going to trigger it if either a servo 1 or a servo 2 is missing. So we can say if not, maybe servo 1, or not, maybe servo 2. Because if either one of them is gone, we're just going to skip this control cycle. And so we'll have to make a missed replies. For now, we'll increment our non-existent one, and then do the same thing if it's greater than a fun constant. Then we'll print some stuff, and well, our break needs to be up there in the if, so we'll copy that and move it up there. And otherwise, we continue. Now, when we print, it might be nice to know which one was delayed, so we'll use some at least minimal diagnostics here. I'll just print like a 1 or a 0 if each servo was there or not, so we can have some clue as to which one is the problematic one. And so we can just use the ternary operator here to turn those maybe results into 1s or 0s for each one. No, too many single-digit numbers. And then just like before, if we got both of them, then we'll reset our missed replies to 0. And we're going to have to go make our missed replies now. And we're eventually going to want status as well, so let's just copy all 3 of those for this example. Alright, now we can do our fault loop, which is going to look very similar to the old fault loop. The only difference is instead of sending break to the 1, we're going to use a range-based for to send a break to all the controllers. So it'll look just like the set stop we did above. We'll do set break like that. Now, what to work on next? We could start doing the hooking things up or work on the status. What to do next? I guess we'll do the status here. So the status is going to look also very similar to before. We increment status count if it's greater than the period. Then we reset it to 0. And then we can print some stuff. And here there's a lot more to print because we've got things from both servos. We still need to flush though. I'm going to use the same character only trick to keep it on one line. So we'll print the mode from each servo, we'll print the position from each servo, and the torque and the temperature from each servo. But before we can print any of those, we're going to need to have them extracted to print from our maybe results. So let's go up here and make some aliases to our, well, we had V, we'll make it V1. So we can have our two servo values. So those will be the aliases to structures that have the position, velocity, mode, faults, whatever we want to look at that came back from the query. We still need to do a static cast int because the mode is still an enumeration that printf doesn't like. But we'll get the mode for both of them. And then we'll put the whole thing in. So that's what we're just going to do, the position, the current command torque, and the temperature for both servos. Now back up top, we'll fill in the input to the Pinocchio model, which just like before, we have to convert the positions to radians from revolutions, so that's multiplying it by 2 pi. Unlike before, we want to wrap these to fit within, ideally, the minus pi to positive pi range. And it'll actually be slightly easier to wrap it from minus 0.5 to 0.5. So we'll just wrap it before we convert it to radians. And we'll just make a local wrap here, which we'll define in a second. The other gotcha is that the servo 1, Pinocchio is assuming that the 0 is at pointing up, whereas we assume 0 is pointing down. So we'll just add 0.5 to fix that up. Right, so now I'm just going to rename this to call it around 0 because we're really wrapping it to be plus or minus, or within minus 0.5 to plus 0.5. So go up to our anonymous namespace and declare our wrap around 0, which we'll just use fmod like the you usually use. The fmod has the problem that if it's negative, you get a negative value back, so we have to deal with that. So we'll, if it's less than 0, we'll add 1 to it to get it back to be positive, and otherwise we'll return it because fmod could return anywhere between -1 and 1. Yes, and that v should be a v1, but we'll fix that later. And we actually want this to be minus 0.5 to 0.5. So let's just do, rather than being simpler, we'll let the compiler figure out if there's a simpler way to construct this, and we'll just do a second intermediate variable and do another ternary. If it's greater than 0.5, then we'll subtract 1 from it. And that'll get it back to be negative in the way we want. Great, so there's our wrap around 0. Now we can keep our existing call to RNEA, and we have to extract those torques out and put them into our torque command, which we already have the array to hold, so we'll just stick them in there directly because Pinocchio returns them in Newton meters and we need them in Newton meters. And just like before, when we first run this, we're going to want to not actually command anything. So let's just comment out our command feed forward torque and leave it always at 0, and we'll come back and turn that on later. Let's compile this and see what we need to fix, because the compiler will save us from finding out at runtime. So 62 looks like we passed in v, but then assumed we passed in value. And then line 112, that should be a singular canFD frame, not a canFD frames. And is there anything else I can, let's just try that again and see what's next. All right, we've got a problem in the printf format on line 164. Looks like the mode should have a D on it there for the other position. And then the set break needs to be a C set break, not an S set break. And we forgot to return from somewhere. Where is that? Yes. Need to return that empty optional rather than just evaluate it and then return an undefined value. Okay, I compiled. Let's try running it and see what we get. It looks like it's running. And if we move it positive, we get a positive torque on the first link. And if the second axis is floating, it requires pretty close to zero torque. The torque on the second axis goes up when it's positive, and when it's negative, the torque is negative. And the second axis is still close to zero when it's dangling, which is exactly what you would expect. So that looks like it'll do the second axis alone. So the second axis 0 requires 0. And if we go all the way up to the top, then the first axis is back to 0 again. If we go okay, if we go positive, we need negative torque, and if we go negative, we need positive torque. And if the second axis is straight up and down, it's 0, which is just what we expect. And if it goes, yep, all those signs look totally reasonable. I think we're ready to go and give it a try and see what works. But before we do this, let's put some actual torques in, but let's also do our same bit of reducing the mass so that we don't potentially have a positive feedback scenario. So we'll just make a fudge factor here of 0.5 and multiply that by both our masses. Compile it, and this should actually apply force. Roughly half the force. Let's give it a try. Run, and sure enough, it's applying torques. It feels lighter. It's not weightless, but it definitely feels like it's helping me lift it up. So that was the counterclockwise, now clockwise. Oh, it similarly feels like it's, even when it's fully extended there, it's lifting it up. And we'll try again this direction. Doesn't take nearly as much force as it did before. Alright, I think that's working. Let's, just like we did before, we'll bump up our fudge factor to get closer to 1 and see if it looks like it's working. So we'll go up to 0.85, try it again. Ah, yes, that's much lighter now. It still has weight, but I can like toss it and it doesn't fall down immediately and rock it to the bottom like it did when it was actually unpowered. And so it feels like you're, loping along on the moon now, rather than hopping up and down on Earth. All right, let's. But I think that second link was a little bit. There's too much power on the first link and not enough on the second link. So let's tweak the masses to try to get it a little bit more balanced. While we're still at our 0.85 fudge factor. Yeah, that's feels a little better. You can feel it dangling off our finger. You can tell when it's dangling off my finger because it just barely scoots along. Alright, so now let's go and up our fudge factor and get it closer to what should be the break-even point where it actually balances out. Alright, let's see what this does. That is very light touch required. It doesn't take very much to hold it up. It's not going to stay still, but it doesn't... other than that case, right here, it does pretty much stay still. It's a little bit asymmetric. I may not have quite gotten the position calibration even on both sides, but yeah, this is definitely very lightweight. It's just barely floating around. We'll play with this a bit more. This is pretty amazing to play with. It just feels like it's an eerie floating thing when it should not be, because gravity should be pulling it down. You can just watch it jostle around off my finger. It's hard to see in the video, but it's barely making a dent in the flesh of my finger as it's wiggling around here. It's not quite as surreal as the one-axis one, and probably would be better if I spent more time tuning the masses or calibrating the zero offset, but it's still pretty impressive. Yeah, you could play with this all day long. Any orientation, it feels like there's basically zero weight on it. And it's still, because of those direct drive brushless motors. It's very responsive. We could certainly add damping, but there's no damping now, so it feels like you're just wiggling around something that's frictionless and weightless in space. That's it for both examples. You can check out the finished source code at the link in the description below. If you want to show off what you've made, try out something similar yourself, or just have questions about using the C++ API, hop into the MJBots Discord and ask all the questions you want. That link is in the description too. Thanks!